Good morning, everyone. Today is February 9th, 2019, and this is the John Chappell Natural Philosophy Society Saturday Science Chat. I am your host, Franklin Hu, and today we have special guest. Clive will be speaking to us about time dilation and reciprocity and the errors about that. So, Clive, why don't you take it away?
Thank you very much. Well, I'm going to say good morning because, I'm going to say good afternoon because it's 3 o'clock. I'm in the UK. Okay, I'm going to examine the errors in the explanations of reciprocity and the consequent miscalculations in the concepts of time dilation and length contraction in current physics. Since Einstein, reference frames have played a crucial role in relativity, especially when considered as being an observational perspective in space, which is not undergoing any change in motion, that is, obviously, acceleration. Reference frames, it is maintained, determine differences between the time circumstances of two observers, with the prime system being in motion relative to the unprimed system, having a constant velocity only along the x-axis from the perspective of an observer stationary in the unprimed system. This has given rise to the belief that a moving clock doesn't move so fast through time as a stationary one. Or a clock sitting at rest, being the outside observer, travels along in the time direction at the speed c with no motion through space. However, at the time when Einstein was postulating these considerations, he was under the misapprehension that the universe was static.
Clive, can I interrupt you? I can hardly hear you.
I find the volume rather low as well. If you could speak up a little, please.
I wonder if I put mine's absolutely at the top. If I'm closer to the screen, does it help?
That helps if you get closer to the microphone. Okay. Thank you. I'm sorry to interrupt.
No, that's not at all. Okay, I was just saying that when Einstein posited these considerations, he believed the universe was static. But of course, this was before Stephen Hawking, the notion of the Big Bang and Hubble. And of course, now astronomers have now calculated a boost in the universe's current expansion to an acceleration rate of 45.5 miles per second per megaparsec. So that the velocity at which a distant galaxy is receding from the observer is continuously increasing with time. Now, my first slide, which I hope you're seeing, and I'm presuming that everyone knows what this is now. Einstein posited that a light clock could demonstrate the difference in time as experienced by two observers, one being at rest and the other being at motion. And he employed Pythagoras to use the right-angled triangle equation to demonstrate these differences in experience between two observers. So here, the traveling observer, Einstein would maintain, would see the straight line L, which is a beam of light bouncing between two mirrors. And he imagined these mirrors being on a train so that they were actually traveling. And in consequence, because each mirror would change whilst the light was moving from one mirror to another, he said, okay, the second mirror is out of place. And so in this case, the green light, this is the perspective of the outside observer, the green light would bounce off the mirror, obviously at a diagonal, because the mirror has moved during the passage of the light. And so the outside observer would see this zigzag line of light. And given that light speed is constant, the notion is that the only variable must be time. Time must be the variable issue here. Okay, you should be seeing a slide now of what looks like, or what I've tried to make, like a moving train carriage. The guy in the blue shirt, he's looking at a mirror on either side. And somehow the light pops along. He's always seeing it traveling between these two mirrors. The outside young lady, she sees the zigzag line because the mirrors move during the time of the train moving. So my first looking at this, when I first tried to understand what's working here, is does the blue line hop along with the guy? If not, it must be a zigzag for him too. It's just his perception, the way he looks along, that it appears to be bouncing just between two mirrors, and making that a difference between what the girl outside sees. Now, I thought long and hard about a light clock and thinking what the problems are of making one. And of course, if you put a light bulb between two mirrors, the light bulb is in the way of the beam that's bouncing back and forwards. So my next slide is my conception of this is a light clock that should work. So there's a spark being caused between two front-faced parallel mirrors that are held a particular distance apart. Now, while the battery is connected, a fast-growing sphere of light obviously will expand in every direction from the source. I'm hoping you're seeing this slide. So I'm now going to change them. I'm changing to the next slide, which is it's much more, it's brighter because the light now has expanded and is expanding in all directions from this generated spark. Now, while this happens, it's inevitable that some of the light will hit the mirrors exactly at 90 degrees. There must be some light that hits it and must be bouncing back towards the opposite mirror. And of course, the spark cannot be in the way of the bouncing light because there is nothing physical in the way. So what we should be getting is something like a slide here. When the battery is disconnected, this should be what we get. The generated beam of light continually bouncing between these two mirrors. However, this is a Photoshop image because it doesn't happen. What happens when you turn the light out? When you turn the spark out, it goes dark. There is no continuing beam to bounce. Now, my explanation for that is that the light beam is not at all connected to the mirrors. When the sphere of light expands, it is completely independent of the mirrors. And the mirrors, of course, are attached to the Earth, and the Earth is spinning. And here is an image of the mirrors hovering above Earth. And as Earth moves to the right, the mirrors move with the Earth to the right. And what we once saw as the beam bouncing between the two mirrors has escaped because the beam will not be pulled along by those mirrors. There's nothing to make the beam adhere to the mirrors. It's completely, it's immaterial now where the mirrors are. So if the world turns at 1,000 miles an hour at the equator, and the expanding sphere of light cannot accompany the mirrors, which spin away with Earth and all other matter. So I can run this as a sort of moving slide there. So as the original light beam from here expands, you see the mirrors move and the light is elsewhere, which for the person with the mirrors, it looks like it's been switched off. I'm hoping you're all getting this. I'm hoping that the system copes with the speed I'm moving these slides at.
Yeah, we can see the animation.
Okay, great. So I'm just going to give a quick visual example of this problem. Here we have a man with a gun kneeling on a static train, aiming at a target on an opposite train. Now, while it's still, the chances are this guy is going to hit that target. But inevitably, the bullet fired initially will miss the target if he doesn't pan his gun when it moves. So I'm just going to run. here's looking down at it. The arrow, the yellow arrow is the bullet. And of course, pretty straightforwardly, as the trains move, the bullet's going to miss it. So this is another explanation of why I believe a light clock is just not a possible thing to base a hypothesis on. I think it's very, very shoddy that so much has been predicated on this notion of Einstein's. Now, I think Richard Feynman must have sensed there's a problem with this. So he adjusted the light clock idea to be a beam of light bouncing between a single mirror, bouncing off a single mirror. He had a pulse generator, which you see on this picture as a flash tube, and that sends a light to one mirror and it's picked up by a photocell. So what does Feynman say about this? He says that in picture A on the left, he says, this shows a pulse emitting light clock at rest. This is Feynman's wording. Yes, every pulse will be reflected back to the photocell with the beam being angled thus and with the apparatus being at rest. In the middle diagram, which is Feynman's B, he says this shows that the same apparatus moving to the right and the pulse still being caught by the photocell target. So what has happened? This very clever beam, instead of being directed slightly to the left, has decided to aim its beam to the right to hit the moving mirror. And then that again has bent to hit the receiver. However, from this, he has also come to the conclusion in the last diagram C that this is the outcome of a traveling observer's point of view of light. So this is actually what he's trying to get away with. So in this slide I've got up now, you've got the first one, A, which is still, and the flash tube emitting light slightly left and upwards and coming slightly left and downwards. But what would have to happen with his apparatus is the pulse would have to go up, following the dotted line. It would have to bend to hit the mirror, which has moved, and then it would have to be bounced back and bend again to be received. So clearly, this apparatus is rubbish. In no way does it prove what would happen with a light clock on the move. So what does Feynman say about this? He says an external observer would see the clock going by with the pulse going from mirror to mirror, thus really taking a zigzag path. This is his wording. He does not realize that it would not take a zigzag path. He then says, that is, it takes a longer time for light to go from end to end in the moving clock than in the stationary clock. Therefore, the apparent time between clicks is longer for the moving clock in the same proportion, as shown in the hypotenuse of the triangle. So from the figure, it is also apparent that the greater angle the hypotenuse is, the more slowly the moving clock appears to run. And then he goes on to the extreme conclusion. Not only does this particular kind of clock run more slowly, but if the theory of relativity is correct, any other clock operating on any principle whatsoever would also appear to run slower in the same proportion. This has got to be nonsense. So this is what would happen. I'm just going to run this. So here we have his piece of apparatus on the left, and it's static, and it's bouncing off the yellow mirror. Now here we go. It travels, it misses the mirror. I'll just run that again. I'm hoping you're seeing it on the move. So quite clearly, Feynman's apparatus would not work, and therefore in no way does it prove that there is a difference in time for a moving observer from an exterior observer. Now we come to how reciprocity is used in reference frames. So I'm just going to run that through to get onto the next slide. Here we have Einstein's famous flash of light. It's the train carriage and a flash which occurs within the carriage. Now, because he considers that relative to oneself, one is static, this is the view that Einstein claims to occur. Outside, there's a second observer at rest watching the train pass. Now, a flash of light occurs in the middle of the carriage, and this is seen by both observers. Because relativity's notion of different reference frames between two observers, this is where one can see oneself as not moving relative to oneself, and the laws of physics are temporarily dismissed. So this is the traveling observer. So the flash point, which is the center of the carriage, is considered to move along with the carriage. For the observer on board, the train, the front and the back of the carriage are fixed distances from the source of the flash. And according to this observer, the light will reach the front and back of the carriage at the same time. Well, I'm sure you see what the situation is. The carriage ends were at a fixed distance from the flash when it occurred, but the flash occurred at a position relative to the Earth, not relative to the moving carriage, no matter how it appeared to the traveling observer. The carriage end walls were coincidentally equidistant at the time of the flash, but the true position of the flash source cannot be relative to or tied to a moving carriage. This is rather like the flash in my spark generated between two mirrors. The mirrors dash off and the source point of that light is left behind by the movement of the universe. Now the next one is my view of both observers. Although for Einstein, this appears to be only the understanding of the exterior observer. The exterior observer realizes that the flash occurs where I've drawn the upright pink line. Consequently, as the carriage moves to the right, the left-hand end of the carriage obviously gets hit by the beam of light first because it is moving. The carriage is closing the distance between the back end of the carriage and the flash point. So here we go. This is how I believe both observers see the flash of light occurring. That is, hitting the back of the carriage first and not hitting both ends of the carriage at the same time. Now, it's very odd that this claim is made that there can be a difference in the perception of what a light does for an interior and outside observer, because one of the meta principles of physics is that all laws of physics must be the same in every reference frame. And quite clearly, this goes against that. Right. And the next thing I want to talk about is how this is applied to length contraction. And we have here, I'm hoping you're seeing a slide of a ladder and a garage. And it's claimed that length contraction occurs at speeds close to the speed of light. And the popular explanation of the issue involves a garage with a front door open and a ladder which, when at rest with respect to the garage, is too long to fit inside. Now we move the ladder at a high horizontal velocity towards the stationary garage, and because of its high velocity, the ladder undergoes the relativistic effect of length contraction, and it becomes significantly shorter. As a result, the ladder can, for a moment, be completely contained inside the garage. I think you've got it all in shot there. So there is the garage by frame 6. It's contracted and conveniently fits in Einstein's garage. Yes, the proper length, which is in frame 1, is allowed to travel at 80% the speed of light, I've got it moving as 8 small frames on this graph paper just to keep proportions correct. And according to length contraction, an observer with the static frame of the garage perceives that the approaching ladder is shortened by length contraction. Now, I have to say that perceives is an important word for me, and we're going to see it occurring later. Now, let me just see what I'm going to run now. Yes, so here it is. This is the same thing in motion. Here is the ladder 80% C traveling towards the garage, and it hits the back of the garage, and for a moment it's within the garage, and I'm going to explain this. Yes, when the physics tells us that the back end of the ladder does not know that the front of the ladder has stopped, as all information about the impact has to travel at C. Therefore, the back end of the ladder keeps moving into the garage 80% C until the impact message, which is the blue arrow, which is moving to the left, until that blue arrow reaches the ladder's back end, which is frame 6, and tells it that the rest of the ladder has stopped. So the back end stops too. So I'll just run that back. So this is the impact, and we've got the information being the blue arrow, and that's going to travel towards the back of the ladder to tell it to stop. So the ladder continues moving in, the information approaches that, and here is where the information that the front has stopped tells the back of the ladder to stop. Well, it's called counterintuitive, and it certainly is. Now, the apparent paradox comes when we consider the symmetry of the situation. So now for reciprocity, we must consider the garage to be traveling at 80% C towards a proper length static ladder. An observer traveling at constant velocity in the inertial frame of the garage also occupies an inertial frame where the principle of relativity, the same laws of physics must apply. From this perspective, it's the ladder which is now stationary and the garage which is moving with high velocity. There's a bit of it. It's therefore the garage which is length contracted, and the physics now concludes it's far too small ever to contain the ladder. So this is a drawing of what is considered to be the reciprocal event of this paradox, and it's wrong. I'm now going to show you what the correct reciprocal view would be. I'll run it after I've explained what's happening, but crucial action is missed in the one I've just showed you, because if we accept that when the ladder struck the end garage wall, its front stopped while the back continued to travel by reciprocity, well, the back wall of the traveling garage impacts with a static ladder and stops, but the front of the garage should keep moving at 80C until the information from the impact reaches the garage's front end and tells it to stop. So here is a drawing where I have the information of the impact, which occurs in frame 3, moving towards the back of the ladder, but it's trying to catch up with the movement at 80% C, which is the front of the garage. Now I can run that. So you see that if we are going to believe in reciprocity, the garage is going to stay, the ladder is going to stay the same because that's not the one that's moving. And the garage, the front of the garage, continues to move because the information, which is the blue and white arrow, hasn't told the rest of the garage to stop. And it's not until now that the garage knows to stop. Now, this is what relativity and length contraction tells us. And I can't really believe in this. So just for a moment, I want to consider, supposing we have 1,000 static people watching this ladder and garage charade from an adjacent hillside. What do they see? If they take a photograph, what do they record? Let's add a passing car traveling quickly in one direction past the garage and another car at a similar speed traveling close by in the opposite direction. What do the occupants of these cars see? If the behavior of moving objects, such as the ladder and garage, can be totally modified by the interpretation or the mere perception of any or all of many observers, it becomes obvious to me that this counterintuitive hypothesis is not only completely unwieldy, but it entirely leaks credibility. It must have an infinite number of possible solutions. Right, I'm going to move on, still talking about length contraction. Current physics also believes that close to the speed of light, objects shrink in the direction of travel. And this has led to a belief that we can travel to far distant stars in a human lifetime. However, if length contraction was an assured phenomenon, then this could be a disadvantage for a high-speed craft. Here we have the full-size craft in a fast orbit around the Earth, and as it nears light speed, it apparently has its length shrunken. Here's the shrunken one. Now, a shortened craft will apparently have a greater distance to travel relative to its new size. If the craft has shrunk to half its length, then it will have a prospective journey of twice the original distance. Let's consider an orbit almost halfway to the nearest point of the orbit of Venus relative to our world. If the craft is 250 meters in length, it has to travel about 502 million times its own length just for one revolution of that orbit. Should the craft shrink to half its proper length, then suddenly it has to travel 1,005,309,000, etc., times its new length of the same journey. So again, I'm finding trouble in believing in length contraction. Of course, all this is very, very pertinent to the famous paradox of the twins. Current physics and mathematics demonstrate discontinuous, simultaneous episodes in the life of these two twins. It's accepted that all journeys in space-time are considered equal. If more distance than time is used up by the astronaut, she ages slowly. When more time than distance is consumed by the Earth-bound twin, he ages more quickly. That's the hypothesis. So here we have the stay-at-home twin traveling up the timeline only, and the astronaut twin traveling close to the speed of light, therefore using up most of her space-time in speed. We can see represented that the twins take a different path through space-time, even though they start and finish at the same point. Well, the first issue is the consideration that the stay-at-home twin, of course, he's not static, he is moving. To call him static completely disavows the accelerated motion of the universe now. Excuse me. Also, the above space-time diagram implies that the astronaut travels away from her Earth-bound twin and then back towards him. It is widely accepted that the age differential when they both meet again is attributed to an acceleration away from the Earth, a long and distant cruise, a deceleration towards a destination, a turnaround, and a second acceleration, cruise, and deceleration back to Earth. It is considered that a reciprocal event of the Earth being the traveler and the astronaut as being at rest is unacceptable because of those accelerations and decelerations. If reciprocity was possible, then it would be conceivable that either twin could be older or younger, and of course that's indefensible. So I just want to talk quickly about how reciprocity here has been ill-considered. So here we have an image of a spacecraft traveling towards a distant planet. The universe is shown to be at rest relative to the craft. The gaps between the images of the spacecraft are regular, they're consistent, therefore she is cruising at a uniform speed. Let's see this in motion. Space is still, the aircraft moves. Now, as she approaches her destination, she slows down, she decelerates, and you can see now that the gaps that the spaceship moves forward are decreasing, and that indicates a deceleration as she reaches the planet. I think I can do that in movies. Yeah, so there's a big move there, a smaller as she gets towards the planet she's aiming at. Okay, so that's with the universe being static and the spacecraft moving. But what about the reciprocal event? The reciprocal event is currently disallowed as the astronaut's trip has involved acceleration and deceleration. She can feel herself being pulled back in her seat when accelerating, which apparently cannot apply reciprocally to Earth. I disagree, and I'm going to show you why. Because this allows for the unforgivable assertion that speed changes determine a special direction in space, which is wrong. A direction of the acceleration which the astronaut only experiences when she turns her craft around. So let's just think about it. For a start, it cannot just be the Earth we have to consider here in a reciprocal situation. It's far too selective. It ignores the fact that the Earth is part of the universe and can't be separated from it. The Earth can't change its place in the firmament at the whim of an astronaut. So here we have the astronaut being at rest, and you can see my images of the universe moving to the right. And I think I can move that. So you can see that the space is moving to the right, and as far as my drawing is concerned, the spaceship is static, and it's the universe that's in motion. And this will apply to deceleration. Here is a static drawing of it. So the gaps between the distance of the planet and the spacecraft are not consistent. They diminish as the spacecraft gets closer, but it's space that's moving, not the spacecraft. So here is the version with the spacecraft static and the universe moving. Now, I know that that's going to get a lot of complaint, and so there's a way that I can make this more bearable. If you imagine that we are in our own spaceship, and I've put another space in just for fun, here it's quite acceptable that we see I'm just going to go back to the beginning. We see ourselves as static, and we see the universe moving. This is the reciprocal event of the twins. Now, the outstanding thing about here that I haven't really, and I want to deal with, is the business about acceleration, because I know that this is it's a point that gets argued about. So an accelerometer is a device that measures proper acceleration, that being the acceleration or rate of change of velocity of a body in its own instantaneous rest frame. At any point in space-time, the equivalence principle guarantees the existence of a local inertial frame, and an accelerometer measures the acceleration and deceleration relative to that frame. So if the spacecraft has its deceleration measured in the earlier images, and the universe has its deceleration measure in those later frames, there's no getting around this. Therefore, an accelerator present in either reciprocal event has to register the same change in relative velocity. The accelerometer would inevitably read an acceleration and deceleration, and the astronaut would be pushed back or forward in her seat in either reciprocal events, as the mass of the universe affects the spacecraft in both situations. Otherwise, the word reciprocal has no meaning. When the earthbound twin is the traveler and the spacecraft is considered to be at rest, the space-time distance between the twins must match in both considerations. So here they've got their changed places. So if we all agree that the space-time concept must embody reciprocity, then this graph too must stand and be pertinent. And if the two events are truly reciprocal, then time dilation and indeed length contraction must match and then cancel one another out. Now I'm coming to the realization that space-time diagrams actually dictate content. Implicit in their construct is the fact that the astronaut's journey has to be traveling away from an Earth-bound twin. Even though we know that there is no direction, no up, no down, no left, no right, no forward, no backwards in space. Here is the commonly shown graph for explaining the time difference of the twins. This has the Earthbound twin at rest. He is at the bottom of the time upright axis. where almost all of his allocated speed through space-time is expended traveling through time. And here the astronaut travels at 3/5 light speed. The diagram shows a 5 light-year path on the graph, with the astronaut traveling for 3 years on the outward journey and the same on her return. The upright axis is the time frame of the stay-at-home twin. The orange line is that of the astronaut. Current physics tells us that the blue lines demonstrate the passing years for each twin, revealing the changing values of space-time's relative simultaneity. According to this representation of the twins' experience, by 5 Earth years, the astronaut has lived only 4 years, so that after a 10-year trip on the astronaut's return, the latter has aged by 8 years, and her stay-at-home twin has aged 10 years. However, this seems to embody another piece of seriously conflicting information. She is shown to travel at 3/5 the speed of light. Should she actually only travel for 4 years for a distance of 3 light years, then the speed of her ship must have been 3/4 of c, which conflicts with the 3/5 shown on the graph, resulting in an inexplicable increase in speed of over 10 million miles an hour. Also implicit in a space-time diagram is the assumption that the astronaut travels away from the Earth-bound observer. Inherent in its layout is the predetermined and inflexible notion that an increasing spatial gap is the inevitable product of her journey until she turns around when a decreasing gap occurs. So, as shown in this graph and also the one above, the astronaut's timeline extends at an angle, which indicates her speed relative to c, as she moves away from the upright timeline of the Earthbound observer. Thus, there becomes an inescapable assumption of a growing distance gap between our two protagonists. We are shown that signals from the Earth to craft vary, and also indicates that the craft is becoming further and further from Earth, then closer and closer to Earth. So here's a diagram showing the messages sent from the spacecraft to Earth and how they change once she turns around and starts coming home. Those signals from the craft to Earth vary likewise, and that indicates similarly the distance position of the craft from Earth. So a space-time graph dictates how and where her journey progresses, rather than her journey dictating the construction of a graph. And this most damning implication of this growing distance is that the further and further apart the twins grow, the more incongruent are their time frames. And now I demonstrate the failure of such concept on their graphs. Right, let's take our traveling twin to a distance of 20 million kilometers from Earth, almost halfway to the nearest point of the orbit of Venus relative to our world. And here she begins a circular orbital path around the Earth. Hoping you're all looking at a picture of a spaceship going around the Earth with various distance and figures on it. At this height, the circumference of such a path will be approximately 125 million kilometers in length. Her craft, traveling at 97% the speed of light, would take 7.19 minutes to circumnavigate the Earth completely, keeping to that orbit. Now, how should we judge timings now? With a wristwatch, with an atomic clock, with a calendar? No, I want to use sidereal time. It will be a sensible choice to judge and compare both the astronauts and the homebound twins' timing of the spacecraft's number of revolutions of the Earth per day. So sidereal time is measured relative to fixed stars rather than to the sun. Our astronaut arranges her orbit to coincide with a line of sight to the North Star. Then, from the homebound twins' given observation point on Earth, the North Star will act as the starting and finishing post to be found at the same location each night at the same sidereal time, no matter how many revolutions of the Earth the astronaut makes. Thus, the homebound twin, with his telescope aimed towards the North Star, will see his sister pass by approximately 200 times in his 24-hour day. Whichever way the astronaut may appear to experience her time differently from her brother on Earth while being on the move, she has to note the number of times that she passes a line between the Earth and the North Star. She just cannot pass by this marker more or less times than is noted by her homebound brother. Our astronaut may circumnavigate the globe as many times as required to equate to a distance to a journey to Andromeda, and she may then turn her craft around, undergoing the same acceleration and deceleration as any corresponding and outboard trip to Andromeda, to complete the same number of revolutions in the opposite direction. This is to make exact comparisons with an Andromeda voyage. But will her time experience differ from her homebound brother? It can't, of course it can't. There is no way the twins will disagree about the number of passes the craft has made across the Earth Polaris start-finish line. And don't forget, according to physics, it's the outsider observer's view of a traveling clock that leads him to believe her time runs slow. But there is no way he will perceive her clock is running slow when he can see her pass the start-finish line at times that coincide with his own timings. It will take a desperate and time dilation committed physicist to find fault with this comparative trip. So I ask, how could time be different between our two protagonists? Nothing fundamental has changed between this journey and the journey to distant stars. How can the actual time passing for this astronaut be influenced at all by the opinion of her brother on Earth? Now, the only question I thought that might come up might be the difference between an Andromeda trip and the matching distance orbit around Earth would be the influence of gravitational forces. Although no current interpretation of the twins' paradox addressed this impact of gravitational fields to which the astronaut must travel, I'm just going to look at it. So compare the predictable gravitational experience of the twins circumnavigating the Earth at a radius of 20 kilometers, Sun, Moon, Venus, Mars, etc., with the gravitational influences you would meet traveling to and from the Andromeda galaxy. So apart from the dark matter, gas and dust that pervades most of the universe, her Andromeda route would be gravitationally influenced by 400 billion stars in our Milky Way, Canis Major, Leo 1, 2 dwarfs, Sagittarius, Beta 2, Large Magnetic Cloud, Boots, Small Magnetic Cloud, Minor Dwarfs, Sextants. There's a whole list of the influences that she might meet. So basically, on both trips, there is going to be gravitational influence that has some effect, but not the sort of effect that relativity, time dilation, allows for. So I think we can negate any criticism of my suggested circular trip around our world arising from this gravitational influence. And she should experience no special different problems whilst on a corresponding journey to Andromeda. Here is the Andromeda image and quite a few of the influences that she would experience on the way. Now I want to plot a graph which tries to represent my understanding of sending her on an orbital trip. So we plot the speed of light, the green line, and that takes 5 years along the y-axis to correspond to the 5-year mark on the time axis. We know that during this flight she will cross the Polaris Earth line as many times as has been recorded on Earth. Therefore, our astronaut, the orange line, has to be where the 5-year time marker coincides with the 4.85 light year marker. Those are dictated by her having traveled at 97% C, whereby she has unavoidably covered the lesser figure of 4.8 light years against light's 5 years. However, she is not 4.85 light years from Earth. At her speed, she is 68.66 seconds away from Earth. Incontestably, by the end of this trip, she will still have traveled the 4.85 light years. We cannot move her orange line to the 4-year marker, for example, without slowing her speed down to 75% C. We cannot allow her to travel 2 light years in 5 light years, as the more we move her orange dotted line to the left, the slower we're making her craft. If we place her orange line anywhere below the green line, she is exceeding C. So our astronaut is in her reference frame, and her brother occupies his in exactly the same way as they would should the astronaut be on a straight line journey to a distant star. The layout appears to represent her speed, distance, and space-time, as again it reflects for her the same distance and space-time as she would be spending in a 5-year segment of her journey to Andromeda. What doesn't work is the possibility of applying to the graph a representation of our astronaut sending signals home. A 20 million K above our world, a message will only take 66.66 seconds to reach her Earth-bound brother, and that message time cannot alter throughout her trip. Therefore, this apparently crucial piece of space-time information cannot be plotted on a space-time graph, which, by their very design, imply an expanding communication distance. And I say if a space-time graph fails in any one example, it's completely inadmissible to physics. So all we are left with to discuss concerning the twins paradox is it being the opinion of the earthbound twin that the astronaut is taking a particular time for her journey. And he's probably wrong. It is the opinion of the astronaut that she has taken less time than was previously predicted, and she too is probably wrong. Yet in current physics, so much is predicated on these erroneous judgments of two, yes, only two observers. One more thing, supposing that there were no other observers at all, perhaps following a catastrophic event on Earth, can time be dilated if there is no one to whom she can compare her time? Is she doomed to travel at a proper time now there are no other opinions about what time her watch must be reading? Now, coming to the end now, I'm going to address what I think are probably the questions that are coming up about proofs of time dilation. First of all, mistakes. NASA does not employ time dilating equations in any of their long distance high-speed craft guidance and control systems. The only factor that is employed in their calculation is for information delay. As of 2018, 2 space stations are in Earth orbit, the International Space Station and China's Tiangong 2 Space Lab. These, together with Russia's military station, Salyut 2, Salyut 3, and Salyut 5, and their civilian stations, Salyut 6 and 7, all keep their time in sync with their home countries on Earth. None employ time dilation to any of their activities. The trilateral operation of GPS satellites does not rely upon time dilating factors, as is widely claimed on the internet. Any consideration concerning whether the satellite's clocks are running faster or slower is irrelevant as long as their internal timestamps match. Earthbound receivers locate themselves by knowing the differences between those satellite timestamps rather than by the time of the timestamps themselves. 40 GPS satellites orbit the globe twice in 24 hours. If their clocks ran slow, then their orbit time would be gradually increase putting them all spatially out of sync with one another. So long as the satellite's clocks all run at the same rate, these timestamp differences will be independent of the actual clock speeds. Plus, these times are calculated relative to a reference epoch, which is reset weekly, giving a consistent GPS accuracy of approximately 3 meters. Here, the intersection of time-stamped signals from 4 satellites accurately locate a receiver. There's a close-up. Okay, so that's the end of the slides, but what I'm going to talk about very quickly is just the other famous experiments which are purported to explain time dilation. I think probably the most famous is to do with muon decay. Both the muons that are taken to speeds close to that of light in the particle accelerator and those muons which actually streak to Earth all appear to live longer than their expected time before decaying. Stanford, California provides the reason for this increased life of those accelerated muons. As an object increases speed, so it also increases its energy. It acquires kinetic energy, energy of motion. Energy is assumed to possess mass. Their experiment proved that muons traveling at a speed near that of light increase their mass by 40,000 times. This additional mass is the reason for an extended decay time, not that time dilation has extended the muon's lifespan. The next one is Haffley and Keating. So many faults have subsequently been found with this experiment is now completely dismissed. But in 1971, 4 atomic clocks were flown on a Pan Am flight, and time differences between those and the US naval station's atomic clock were recorded. In fact, 4 atomic clocks were flown to average out their timekeeping. At that time, these clocks were large and required constant near zero temperature and constant pressure to function, neither of which were observed. The whole experiment, their procedure and results are now recognized to have been riddled with inaccuracies. The National Physical Laboratory. Both the National Physics Lab and the Paris Observatory have attempted to prove time dilation by comparing and analyzing strontium clocks frequencies situated at different latitudes in different parts of the world. Synchronized lasers were employed through optical fibers in order to determine any frequency interruptions. Having predicted a difference of 5 nanoseconds, however, no consistent records have yet to be attained. The University of Maryland. Results from their experiments are no longer accepted because of the irregular use of atomic clocks. Michelson-Morley. The incorrect use of non-applicable results. The Mossbauer experiment. This was an ether drift experiment. The drawbacks include the limited number of gamma ray sources and the requirement that samples be solid in order to eliminate the recoil of the nucleus. Ives Stilwell. Direct comparisons between the longitudinal and transverse mathematical predictions under the specified conditions of the experiment are proved to be invalid. GSI Helmholtz Center. Flaws have been discovered in the procedure and results of this experiment as it exploits a weak decay involving the production of an electron neutrino where attempts were made to relate the observed oscillations to neutrino oscillations. The Paul trap experiment. No consistency has been found in their results, and the inaccuracy of their figures is thought to be because of the wrong decision about the stationary ion. Penrose's Andromeda Armada, now accepted as nonsense. Atomic clock ensemble in space. So far, no helpful data supplied. Gravity probe A and the Pound Rebka. These were both questionable experiments to prove gravitational time dilation, and they're not really relevant here. So, ladies and gentlemen, that is the end of my talk, and I'm going to try and find my way back to you. Here, great. And if there are any questions, I'm ready.
All right, Bill, you've raised your flag. Go ahead.
I was trained as a theoretical physicist and worked at accelerator centers and places like that for my PhD. And I think a lot of people do not realize that our scientific method was changed from the days of Isaac Newton to be the existential scientific method. And what they changed when they did the existential scientific methods, they removed the role of logic as you are applying it from science. And then that was changed again in the 1960s to the postmodern philosophy of science, which basically put all different fields of science in different silos. But so what you're showing here is that if you examine the data logically, it's inconsistent with the theories, and I agree with that. And we need to get theories that are logically consistent. But the person who published the book on how to do that was Isaac Newton, and it's called Mathematical Principles of Natural Philosophy. But we do not follow that today. And a lot of people have asked the question, well, why don't we follow that today? What happened from the time of Isaac Newton that caused the scientists to want to remove the role of logic from science? And so that is the real question. We're seeing that you're showing that there's logical inconsistencies here, and the question is, why did we do that? Why is the politically correct science not using logic properly? For instance, Einstein's theory of special relativity and also general relativity each involve at least 5 assumptions that are known to be false. But we don't falsify the theory because its assumptions are false. Now, what you're showing is that some of these assumptions that are involved, when you apply logic, they don't agree. And so that's what seems to be going on.
So Clive, did you have a comment? Well, Harry.
Sorry, I'm not getting anything.
Okay. I wanted to ask the question before we start, Bill. I think you hit the nail on the head. Unfortunately, in the context of this discussion, I don't think my question would be, the first question I think ought to be asked is, how many people here believe in that special relativity is correct as a theory, and how many don't? And if you believe in the theory, what is your objection to this presentation?
Well, I believe that the experimental equations appear to work for time dilation.
You're breaking up.
Yeah, there's something wrong with my audio here. Is everyone muted?
Well, let's hear from some other people other than you, Franklin. I already know what your position is. Do we have anybody here that thinks special relativity is correct, and that that's willing to defend special relativity?
I'm not sure whether I do or not. I can tell you what I think goes on and how it gets misinterpreted. I don't think I agree with special relativity, but maybe I do by accident.
Well, do we have anybody who's a believer?
We've got Einstein.
Einstein, is he a believer? I don't know.
Well, he was wondering why people with English accents are always attacking his theories.
Yeah, I saw that. Well, I mean, if he doesn't want to speak up and give his opinion, that's okay. But otherwise, it looks like we don't have anybody willing to speak up and defend special relativity.
Of course not. We're a dissident group. But Clive, so you would you at the end of your talk, you gave all this gigantic list of experiments. So you think that basically all the time dilation experiments are wrong? You just don't believe it happens at all?
No, that's quite right. I don't believe it happens at all. I mean, I think that there's a great emphasis to try and make a name for oneself by proving things that Einstein said to be true. And I think that a lot of these experiments are done by people who want to be the person who has proved time dilation and proved that Einstein was correct in many of his theories within relativity. I have yet to find a proof that works. And because there's so much written about our possible ability to reach distant stars, either through length contraction or through aging more slowly, I'm sure that anyone who actually attempts to do that is going to be extremely disappointed, because I'm absolutely sure that these ideas are totally non-workable. They're just wrong.
Okay.
What does time dilation mean? I mean, you started off your talk, and my question would be, when you talk about time dilation, what does that mean? What does length contraction mean? You based your whole talk on a presumption that those are meaningless meaningful words and apply in some way to some kind of meaningful physics concept. And so, in my opinion, until you can really pin down what those two things mean, you can't say you proved it or disproved it one way or the other. So what does time dilation really mean?
Well, I think there seem to be innumerable books written about it, innumerable spots on the internet, that the belief that time can differ between two observers when one is considered to be static and the other is considered to be in motion. And the triangular drawing that I got from Einstein that I showed first is the explanation for that very difference. And I think that there will be, and there is, no difference in time between any two observers, no matter their position, no matter what speed they travel, because actually when you come down to reading about time dilation, it's always one person perceives the other person's clock as being different. And a perception of someone's time being different doesn't allow that other person to travel for 3,000 years in space and only age by 20 years, which is the most common prediction from time dilation.
So
you have Michael has a flag up, then Ian.
I believe that there are differences in time, and of course I'm an ether theorist, and I believe that vibratory rates differ between quantum etheric realms, and that vibratory rates can go faster or slower. And that what happens when, for example, this astronaut was going from rotating around the Earth and passing the same line with the star as the twin observer on Earth, what is actually happening is that the person in the spacecraft is in outer space beyond the magnetic energizing faster rate time, and is actually experiencing his own energy level. His event is horizon is slower, and that this is what determines. It's not the relative positions of solid bodies or perspectives of human observers that controls the time. Has nothing to do with it. It's all at a much more level of energy and relative quantum etheric interactions but I do believe that there are differences in time, that the time goes slower. If you could go far away from all the magnetic and energizing influences of cosmic bodies and really outer space, it would go much slower because it would be more etheric. I mean, that's just in my ether theory.
Okay, Ian, you have a flag?
Thank you, Franklin. Clive, slightly at variance with the previous last comment, I actually support your central thesis that time dilation doesn't exist. I mean, I don't think time itself slows down any more than space changes. And I can establish this succinctly by saying it's an unnecessary hypothesis to explain the experimental results we have so far. Basically, answering Harry's earlier point that I don't accept SRT. I don't think it's essential to explain the phenomena. And in fact, furthermore, I would maintain that it is disproved by experiments if analyzed properly. However, I do think that there is experimental evidence to establish that atomic clocks tick more slowly in certain circumstances. One being when they start moving relative to, let's say, an etheric frame, because I would use that terminology as well. We talk about, say, the Earth being entrained in an etheric flame. When the clocks move relative to that. I mean, in GPS, even where you have not actual time, but time differences in the satellites which are used for GPS, you find that actually the time differences are less than they would be on the Earth. And the other circumstance where that would apply would be in a reducing gravitational field, where the clocks will actually vary in rate because they won't be bound. So now it's somewhat surprising, perhaps, that the slowing, not of time, no time dilation, I'm totally at one with you there, but the slowing of the atomic clocks seems to be dependent upon the Lorentz factor, which is exactly the same as the so-called time dilation. That seems to be a rather strange coincidence. But on the other hand, you could say, well, it's really, if you're talking about electromagnetic radiation, you're talking about C plus V and C minus V effects. And if you multiply the two and you get the sort of geometric mean, you're back to the Lorentz transform. So perhaps it's not so surprising, but I just indicate that there is a fundamental difference between a physical effect, that the actual frequency change in the atomic clock is a real physical effect, but it's nothing to do with time dilation. So I'm wondering what you think about those comments. Thank you.
Well, your comments about gravitational time dilation, I mean, I don't know about that. I look at it often, and I haven't really got an opinion about it. I do think it's quite strange if it means you can walk up a mountain and walk into the future, and look down from the mountain and see people in the past. I find it's an awkward concept, and I'm not quite sure how gravity itself could alter how a clock works. So it's not really, it's relativistic time dilation that I have agree that gives me grief, whereas gravitational I'm not sure about.
And there I agree with you, but I just conceive of the possibility of gravity as affecting the vibrations of an atomic clock and therefore having a physical effect on it, whilst agreeing with you that it isn't at all a time dilation, or indeed moving in time from past to present to future.
It's interesting what you say about atomic clocks, because as I understand it, that they're reckoned to be, because they mostly to do with the decay of cesium, that they are unaffected by speed, distance, height, because when people are doing proofs with atomic clocks, sending them up in rockets and traveling them in planes, implicit there is a belief that they are going to work in the same way as they would laboratory on Earth. I thought they were meant to be foolproof and work the same wherever they were.
Now, that's an area where I'm just not sure about, but I would guess that that atomic clocks are not immune to gravitational effects. So theoretically, if you were put an atomic clock in a balloon and and then bring it back down to Earth, you would find that the clocks would have changed in time. So I don't think they're immune.
Due to what?
Immune to gravitational effects, that you would see that effect. Certainly in GPS satellites, they always famously say that they have to retard the clocks at launch so that when they get into position, they're running at the same rate or something like that. Although I wish we had someone who was an expert at GPSs, because I've seen a lot of these discussions, and what I understand about it is that these clocks are just simply engineered to run at exactly the same rates to the earthbound clock. But in order to do that, they do have to apply constant corrections to these clocks. They would just not naturally maintain the same clock tick.
Well, Franklin, no two clocks ever read the same time. I mean, come on. You know, that's what
GPS is designed to do. In order for
now,
GPS
hold on. You're making statements based on you don't know what you're talking about.
No, in order for GPS to work, all the clocks must be absolutely synchronized.
Stop.
That's fact.
Stop. What the engineers do is they set the GPS clocks in orbit so that they keep the same time as the clocks on the Earth. And if there are any errors, they adjust the GPS clocks. Okay, so that's all there is to it. It's nothing more than the time is the same by fiat. So time is really basically what you say it is, because you say, I have a clock that measures time, and the clock is a correct measure of time because I say so. So it's nothing, time is nothing more than a fiat declaration. Okay.
Well,
once you understand that, then you can understand how GPS works.
Yeah. So what you're saying is correct. If the clocks were to drift, we would force them back into synchronization just by commands that we send from the Earth saying, okay, that's the wrong time. Now you need to be this time in order to be the same as everybody else. And they apparently they have to just keep on doing it.
You don't really understand. That's only done for the very small errors that occur, because no two clocks keep the same time. Okay, once you understand that fact about clocks, then you realize that time is really a definition and not a physical thing.
Well, I would agree with that. But we're just talking about in the practical terms of GPS is that
as a practical matter, what they do is they adjust the clocks so that the clocks in orbit keep the same time as the clocks on the Earth. That's basically all it does.
Yeah, all the clocks. And that way, that establishes an absolute time frame that you could measure all time in the universe against. That is
Correct.
Basically immune to, I don't know, gravitational or velocity effects, as long as you're on the Earth.
The problem is that the people who support relativity say, well, GPS proves that relativity is correct because you have to adjust the clocks to read different times. Okay, or the clocks would read different times if you didn't adjust them to read the same time. And so they say that proves that time is different. No, it doesn't prove anything about time. It only says that the clocks are different.
Yeah, the clocks run differently. If I have a very inaccurate wristwatch and compared to a very accurate digital clock, is there any kind of time travel going on between those two? Because one of them says 12 o'clock and the other one says 12:05. And I would say, no, that's just a difference in the runnings of the clock and not any difference in time. So, get to what you're talking about, what do you mean by time dilation? And that would kind of mean if you have two very, very accurate digital clocks and you can exactly characterize their drift rates, can you make one of those clocks be in some situation situation where it is like running faster than the other one when it would normally not do so. So if I were to take my digital watch and then I stick one, I mean, some people have proposed doing this, sticking your digital watch in the front of your car and driving it around. And then when you come back, you should be able to actually tell a difference in the time between the one that was driven around compared to the one that's just stayed at home. So that I believe is what they talk about as time dilation. Now, me personally, I think those effects actually do occur. So if I were to take a digital watch and then, I don't know, just like put another one in a drum and just spin it around as fast as I can, that I would eventually find that the one that was spinning around in the drum is going to fall behind the one that was just sitting stationary on my wrist.
Let Clive speak. He wants to say something.
Well, I was going to come in just about first of all, the GPS, because the internet is full of information, like because of gravitational time dilation, the clock would be so many nanoseconds ahead, and because of relativistic time dilation, it would be behind. And they've calculated a number that satisfies them both, and they alter the hertz of the clocks to run slightly slower. This is completely wrong, but the number of sites and number of books that claim that the Lorentz transformation is embodied into the mathematics of working out GPS clocks.
Well,
is wrong.
here's the bottom line. If I have a clock based on a quartz crystal, and the quartz crystal's oscillation frequency is a function of temperature, if I put the clock in an oven, put my clock in the oven, and it runs slower or faster, does that mean time changed for the watch? And does that mean that temperature changes time?
No,
that's what a refrigerator does.
Temperature changes your watch.
Right. So
yes, they make two claims.
Different because of temperature, or did temperature change the operation of the watch? Okay.
And in explaining the GPS, they confuse a physical effect, as you're saying, with time dilation, time itself changing. But the other thing that's commonly claimed is that the Sagnac correction, which is basically a correction for the spin of the Earth, is relativistic. It's nothing of the sort. So those are the two erroneous claims that are frequently made.
Well,
you have to define what time. Time is a relative rate of change, so you always need two clocks to measure time.
Well, the weird thing that I find is I do believe that the Lorentz factor does have to be used in things like GPS and whatnot. But the thing that they find is that you have to use the particular reference frame, which is the Earth-centered reference frame, which is just the point you would get at the center of the Earth. If you consider that motionless, then you can make your calculations of time dilation based on that frame of reference. This is why we can detect the spin of the Earth, but we can't actually detect its orbital speed. It's as if the Earth were the center of the universe spinning, and we can detect those actions, or like the Foucault pendulum can detect the spinning of the Earth, but can't actually detect the net motion of the Earth through around the orbit of the Earth. So that's kind of a strange thing, that it's either the Earth.
I don't understand what you said.
Either the Earth, that center universe, or somehow time is still relative to the area that's around the Earth, at least for GPS satellites.
Time is an arbitrary definition that's agreed to and established by social agreement. And you also passed over what Cornelius said, which I think is correct.
Well, I think time, for example, we can look at astronomical time, and the time that it takes the Earth to rotate around the sun once could be considered an absolute time frame that we need to pay attention to. That's why we have, like leap seconds. And
well, time, you have to have a master clock, as Cornelius pointed out. Okay, you have to have two clocks. So in GPS, you have two clocks. You have clocks on the Earth, which are taken to be the primary or the master reference time. And then you have the GPS clocks, and the GPS clocks are slaved to the master clocks on the Earth. And when that is done, they take out all of the changes in the clock rates due to the physical effects on the clocks that are in orbit, and they try to minimize those effects on the clocks on the Earth so that all the clocks on the Earth supposedly keep the same time within a certain margin of error, and all the clocks in orbit keep the same time within certain margins of error. Then it turns out they can make the measurements and make the GPS system work as long as the errors are small enough. Okay.
Yes, but
What
we've moved into talking about is how we can make certain changes or adapt certain things just to make time convenient for ourselves and to use it. But the thing about time dilation for me, that it violates the very notion of what time is, that time can be significantly different between two people according to their motion relative to one another. And that I just won't accept.
Well, I don't know that anyone says that.
Hold on here. What they're doing is they're using a person's lifetime as a stand-in for a clock, okay? And because they've used the issue of lifetime as a clock, see, being alive and existing as a human is essentially basically what our intuitive notion of time is. So time is essentially an intuitive notion that we humans have because we're alive and we exist in time, whatever that means. You understand what I'm saying? So to say that a person can travel through space, you know, and for 200 years relative to a person on the Earth and come back, you know, only aged 5 years, and the other person is dead because, you know, he aged differently. That's sort of, you know, that whole argument is really based on a lot of fallacies, but the reason it resonates is because it goes to the intrinsic concept of what we humans perceive as time relative to our lives.
Now, I personally would believe that time is absolute and that there exists some master clock in the universe which clicks at exactly the same time everywhere, but that these effects that we see in atomic clocks are just due to the malfunctions of and inaccuracies and foilabilities of these mechanical devices to keep time. And that when we have things like, even like Harry's talking about extended lifetime, I mean, if we were to perfect animation, reanimation technology, and I were to like freeze myself for 5 years, and then reanimate myself 5 years later, and I would look 5 years younger than everybody else, does that mean I travel time? And some people would be confused and say, yes, you know, your time was different. But no, the time was the same. It's just that your mechanical processes were slowed down. And so I would think like all these time dilation effects are more mechanically slowing your whatever processes that happen to your matter are happening. So that's my opinion, is that when we see these time dilation effects, I believe they do happen, but they're more like, you know, sticking meat in the freezer and preserving it than any kind of actual time extension. I think if you were to have a really good accurate clock that clicked on the universal clock, you would see that exactly the same number of ticks happen for the frozen meat as to the fresh meat. That would be my opinion.
Well, yes. I mean, it is quite possible that if you had an astronaut voyaging into space, that his the frequency of the vibrations of his cells and perhaps even his heartbeat and so on could be decreased slightly, and he might actually live a little longer than had he remained on Earth. So, but that's a physical effect. It's not a sort of a change in time itself. But there's one other problem which I think Clive brought out, which is very problematic with relativity theory and the Lorentz transforms, and that is that they are perfectly symmetrical. So these physical effects are not symmetrical. I mean, you're not saying, oh, well, from the point of view of the man who's gone into space, whose organs have decreased in frequency, the person who stayed on the Earth has also decreased in frequency, and it's only an accelerative effect which would show any non-symmetry. We don't say that. So that is the basic contradiction in the whole Lorentz transformations which are used in special relativity. And also, as we agree, confusing a physical effect with sort of a change in time or a change in space itself.
Well, I think we're back.
I
We need to go back to what Bill said. I'm getting an echo here. So what Bill said is there's a flaw in the scientific method, and that's what the issue is. The issue is there's a flaw in the scientific method. The theory, the special relativity theory, is defective. It's completely defective. It's null and void theory. It's not correct at all. But when they do experiments, they say, oh, aha, we can interpret these experiments to show that time dilation really exists as predicted by Einstein in his theory. And because they only do these numerical comparisons, and they don't really look at the logic of the theory, and they don't look at the logic very closely of the experiment, they proclaim that Einstein's theory has been proved, and it's all based on a false philosophy of science and false logic. Now, the question is, why are we still believing in this when we know that it's all just bogus and untrue?
Well, it is amazing because, I mean, if you take eminent physicists like Brian Cox and Kip Thorne, they use the Lorentz transformation to allow in their suggestions that an astronaut would be would live for 20 years, whereas somebody on Earth would live for several thousand. So, I mean, if the Lorentz transformation allows for that, then the Lorentz transformation is complete rubbish, because that it's more than counterintuitive. It's just not going to ever happen.
Well, I think Bill can speak to this, but the thing is that this Lorentz transformation,
hold on.
the change of mass is intimately required in order to get your particle accelerators to work. So there's definitely something going on there.
All right, what's the fallacy in what you just said, Clive? You know what the fallacy is? The fallacy is they're never going to do an experiment where they send somebody out into outer space and he comes back younger than he's supposed to. They're never going to do that experiment. So that is complete fantasy. Okay, so what they
do that because we can't go that fast.
Well, it'll never happen. Okay, so the whole argument is a bogus argument based on the fact that it's not provable. You can't prove it.
You're right.
It's not provable. Okay. So
my comment was that thought experiments aren't actual experiments and shouldn't be thought of that way.
That's a fallacy in the science that they're doing. Why are we allowing them to do fallacious science? That's the question.
See, we've got Alistair. You got your flag up? Go ahead, Alistair. No? Bill. Go ahead, Bill.
I was going to comment on the experiment with muons, which have a decay half-life. If you accelerate the muon, it has a different decay half-life, and it agrees approximately with relativity theory, but it also, if you look at the experiment more closely, you find that the muon, as it is accelerated, shrinks in size. Its diameter reduces, radius reduces, and it's more tightly bound, and that's when it lives longer before it decays. And so we have a physical explanation for the change in the half-life, and then we have relativity theory, which would give us an approximately same result. And so what we do is we throw away some of the physical information we got from the experiment if we want to keep that theory in place. And so what you find is we do this consistently all the time. For instance, in the case of general relativity, when we're trying to explain the high speed of the outer arms of spiral galaxies, we can't. And we can't get it right. So what did we do? We, instead of falsifying general relativity theory, we invented dark matter and dark energy. And then with the combination of dark matter and dark energy plus general relativity theory, we can explain the velocity of the outer arms of spiral galaxies. And then you ask the question, well, how much of this dark matter and dark energy is there? We've never seen it before in an experiment. And the answer is, well, in order to get it right, you've got to have 96% of the universe is dark matter and dark energy, which you can't see, and 4% is regular matter and energy, which you can see. And so why did the scientific community go in that direction? Why didn't they falsify the theory of general relativity and find a better theory?
We're sheeple. So Jim has got a comment.
Yeah,
Jim.
I think I posted a bunch of comments. The problem is that when they did the Michelson-Morley experiment originally, they got the null result, but they were looking for an orbital effect, 30,000 kilometers per second. Now, ring laser gyros, Michelson Gale, even GPS really shows that the velocity of a stationary, geostationary laboratory with respect to the ether is just the Earth's rotation velocity of 350 meters per second, which Michelson-Morley type experiments have not been able to detect. And that's the reason that we're in this mess with special relativity. If they could look for that, the explanation that there are different physics involved between first order type attempts to measure the velocity of light versus second order attempts using two-way light reflecting paths is what everyone is missing.
Well, I have a solution to this. I'm proposing that we have the experimental duality in trying to measure the velocity of the Earth through space. And we use the philosophy of Copenhagen philosophy, which is we say that whatever experiment you do determines the outcome as the result. So in particle physics, they say, well, if we do this kind of experiment, it's a wave. And if we do a different kind of experiment, we call it a particle. And so they resolved this fundamental conundrum that they had in physics by doing that. So I propose that we do the same thing for these Michelson-Morley experiments, and the whole problem will go away.
Actually, the whole problem would go away if you put one on a spacecraft, which has its own velocity relative to the ether.
Basically, the bottom line is that the conundrum can't really be solved based on the current thing.
Just in a more extensive experiment that's looking for rotation instead of orbit.
We've got a couple of flags here, so let's try to get through the flags here. So, Pal.
Yes, can you hear me? I have a question for Clive.
Yeah.
How or where and when did Einstein go wrong? If he were here, could you give him some advice?
No, I'd be. I'd be
He is here.
if he was here. Well, he went wrong in my view because, as I said at the beginning, that he, when he was around between 05 and 15, when these things were coming up, everyone believed that the universe was static. And of course, the whole issue about understanding the difference in time or speed or distance between two separate observers was based on the fact that one of them had to be static. So I would say to him, well, listen, there's no such thing as static anymore, where the universe is expanding, and it's expanding. We can't even talk about inertial reference frames because nothing's inertial. Everything's accelerating. So physics has really changed since his time, and we have to look at the things that he suggested, which were based on the old understanding of the universe, and rethink them, which I hope I'm offering here.
I think my suggestion is a lot better, which is that the problem is that when they thought the Michelson-Morley experiment should have shown that given a positive result, okay, that was a problem because the Earth had to be moving around the sun, and they had already proved that the Earth was moving around the sun based on the aberration of stars, okay? So you have two basic measurements that contradict each other, and the solution is to impose some kind of wave-particle conundrum of duality. And you say, well, both experiments are correct, but, you know, and they both can't be correct at the same time, okay? What Einstein did was he tried to say that both observers can both be correct at the same time when that's an impossibility.
No, the answer is that
Alistair has got his flag up, so I want to make sure he gets a chance to speak.
Woohoo! Yeah, I had drifted off almost a little there. It was a long wait for my turn. So I'll tell you, and I'm pretty darn sure that my my way of thinking about it is correct. And I'm an etherist as well. My ether is completely filling space, and it is made out of Planck scale particles that are never created and never destroyed. They always existed and always will. So from their perspective, they're timeless. Time means nothing to them because they never start, they never finish. They always are. And then everything that we experience as being things are made out of balls of, you could almost call them balls of light that are imbalances and counterbalances orbiting each other. And so when you take an atom and you move it out into space, it expands, and therefore, since the velocity with which the imbalance and counterbalance are orbiting each other is now traveling around a larger radius, and so each orbit takes slightly longer, and so it will appear as though time is dilated, but what's actually happening is that anything that we think of as existing has a start and a finish. At some point in time, it came into existence. An atom came into existence, a cell, a planet, everything that we think of as being matter came into existence at some point, and at some point will cease to exist. So it has time, and it has rate of progression through that time. And so you can break that up into chunks. So when we think we're measuring time dilation, we're not actually measuring time dilation, we're measuring a difference in the rate of operation of the local object. In the case of the GPS satellites, the clocks are now operating at a different rate because all of the matter that makes them up, which isn't physical, all of the imbalances and counterbalances that make them up are now a different size, a different orbital radius, and therefore are operating at a different rate relative to what they would be operating at if they were in a different environment such as being on Earth instead of up in space. And so the phenomenon of time dilation is correct, but the reasoning behind it is incorrect. Because when a satellite orbits the Earth, from Earth you can observe it the entire time. And so from Earth, you can calculate its distance, you can calculate its velocity, and you know where it is, when it is, and how fast it's going. And so you can calculate its speed, whereas the clock on the satellite itself, relative to the clock or relative to the calculation being done on Earth, if you had a speedometer on the satellite, it would read wrong because it's operating now differently because of being in space. So when they say that the clocks are identical in operation, yes, they are when they're in the same environment, but when you take them and put them in two different environments, they'll have different rates. And that's what happens. And that explains our experimental results without saying, because you can't argue with experimental results. It doesn't make any sense to do that. When you observe things repeatedly, then you have to recognize, okay, well, that is a fact because we can repeat it over and over and we can predict it and it occurs.
So is Einstein right then?
Yes and no, because he didn't know that there was this timeless ether to contend with. So he made up the way he conceived time. We used it to calculate and we decided there was a Big Bang, but the Big Bang never happened because space is full of timeless particles. Our concept of time is broken. Does time dilate? Yes. When something goes faster, does it get shorter? Yes. But that's not because of it's for a different reason. It's because it's made out of light. So if you take something made out of light and you make it go faster, it's going to get shorter, but it can never get to the speed of light because it's made out of light. So the time dilation contraction thing, it only holds true within a certain, within like it doesn't hold true indefinitely. Because as you go faster towards the speed of light, the ball of light that everything is made out of, they're just going to come apart.
Okay, so we have our other etherist, Michael Antesky.
Well, in my ether theory, originally it was a universal oscillation, which transitioned to a vibrational elemental units independently vibrating contact resonance between the units. But these are elemental units, and they would have been the basic building blocks of everything from then on. So the idea of a vibratory rate is logical because it goes back to elemental universal ether and the elemental building blocks of everything. And so you could have a vibrational rate which affects time, the passage of time, and the rate of sequence of events of any larger bodies would be influenced by this vibratory rate because it's all part of the same thing.
All right. Well, it looks like we're getting towards the end of our time here. So I kind of summarize a little bit here with Clive. I kind of made some notes in the chat along the way. So Clive, you started out by showing this whole light clock thing. Now, basically, you think this is just a bunch of baloney that you can't really measure time with, I don't know, like light beams. And I would kind of agree with that, although it came up with certain formulas, and it seems to agree with certain experiments, like Bill mentioned, the muon lifetime. So even if that whole argument is just logically a mess, there would be still these other experiments which would tend to confirm this Lorentz transformation thing. which I don't know why we attribute this thing to Einstein, considering we called it the Lorentz transformation. We should be saying Lorentz is wrong and leave poor Einstein out of this.
No. See, now you're saying things that are wrong.
Well, I'm just trying to bring up a little point.
The Lorentz theory is different from Einstein's theory. Lorentz had a kind of an ether theory. So his theory wouldn't be wrong. The problem with essentially Clive is right here to a certain extent. And what I've been trying to say, which you've been ignoring, is that what the light clock says is that when one observer sees the clock running slow, okay, but if we switch observers, it's switched around, and now the other observer sees the clock running slow, but he doesn't see his clock is running slow. Okay.
Well, my other comment here was that
hold on.
Even actually made the light clock experiment. Certainly, it's quite possible for us to do that now with high-speed electronics.
Franklin, please stop interrupting.
No, actually, you're kind of interrupting, Harry. I mean, you're kind of.
Please, Franklin, let me just make my point, if you will. Let me do so. Okay, the point is that this idea that the observer A sees B clock is slow and observer B sees the A clock is slow is a kind of absurdity created by the fallacy of the theory, which is, that the
but not by Einstein. My point was that the full reciprocity thing is not in any of Einstein's theories at all.
All right, I'm sorry, Franklin, for trying to clarify the issue. I'll just keep my mouth shut in the future.
Well, I mean, that is a key issue here, which is that this whole reciprocity thing that Clive is talking about, you'll never find it in any of Einstein's papers. I mean, Einstein never discusses.
Oh, you're wrong again, Franklin. Sorry. I wish you would stop promoting your incorrect concepts and ideas.
It is my opinion, but it is Einstein is saying. It is my opinion that if you look at Einstein is saying. I mean, this is a main bone of contention, because Harry, you would say that this whole reciprocity thing is intimately involved in Einstein's theory. I would challenge you to find anything in Einstein's paper that says anything close to the word reciprocity. I would say, and I know you'll not find it.
You've demonstrated, you've pretty much demonstrated why this whole issue and this whole problem of relativity and this whole problem of modern philosophy of modern science can never be resolved, because everybody's got all these misunderstandings, and these misunderstandings just keep the confusion going. And as long as the experts say we know what the correct answer is and you have to believe us because we say so, they just keep the whole theory going when it's just a lot of nonsense.
Yes.
Well, that's the whole irksome aspect of this thing. Now, another thing that I want to bring up is I wanted to ask Clive about the effects of the motion of the media. So, for example, you have the Fitzview experiment showing that you can get a different speed of light in moving water. So certainly the medium affects things like speed of light. Have you considered about that?
Yes, I have thought about it, but I don't actually think that it can be relevant, because the discrepancies between the possibilities of aging and distance and contraction that the Lorentz transformation allows, and Einstein's earlier suggestions also allow, would not be affected by the change of the very small changes of speed through of light through different media. I mean, we kind of take for granted that the speed through a vacuum is the speed of light, and it really doesn't change much through gases or through water. Certainly not enough to make anything of the length contraction or time dilation anywhere near believable.
I was wondering, because I could still kind of believe in time dilation. I think I'm convinced I've seen enough experiments for that to be true, but I haven't seen anything convincing about this whole length contraction thing right now. And I was just very confused about your whole garage and ladders example. And that's probably because it's just complete nonsense. And you're just explaining it's complete nonsense. It is total nonsense.
That is Einstein, though. That is Einstein. I think it was a pole and a barn. And the other one was the train carriage, which also is Einstein's.
Now, I think the only thing is Einstein is like the light in the train. I believe I've seen that, but I don't think Einstein said anything about a pole in a barn. That's probably dissident, is what that is.
No, I've seen it that way as well, with the long thing entering into the. Yeah, I've seen that.
Yeah, but who came up with that? I think that was somebody
Einstein.
else, not Einstein.
Einstein. But I wanted to mention something to Clive, if I may.
Sure.
I watched this MythBusters video about disproving flat Earth and ignored the whole flat Earth thing. But what they did was they took a laser beam, they shone it off of the moon, and then they waited 4 seconds and saw if they got any photons back. And they only, out of the billions and billions of photons that transit there and back, they only get hit by a few. And I wonder if maybe that's because they should be putting their receiver 1.5 kilometers away to make up for the 4 seconds that it's traveling to the moon and back. And maybe that's why they only get a few photons instead of more of them. And I wonder where they do locate their.
They get any at all.
Yeah, that's what I wondered too. But I mean, a mirror coming from the moon, there's going to be a whole lot of spreading out of the light. So you could see why they might get a few. Maybe if they had their receptor 1 kilometer and a bit away, anticipating the motion and the time lag, then maybe they would get more photons.
The thing is that
just that I mentioned that because I found it interesting and it had to do with mirrors and light.
Yeah, the thing is that if there's a mirror on the moon and you point something at it, by the time the light gets there in that 4 seconds, the mirror's moved. I mean, it would have to be a very, very big mirror, and then you wouldn't know what part of the mirror you were hitting, and it would be a miracle if you got in line with the returning photons. It just
that's my point.
They say there's this experiment to make light go faster. They say if you get a laser and you point it at the moon and you pan it quickly across the moon, then the light traveling across the moon is going faster than light. But of course, that just doesn't work. It's just one of these daft things that people come up with to try and debunk several of the laws of physics.
Yeah. The experiment I saw, I mean, they did it at this observatory. They have a a big ass laser, and the mirror that's on the moon, it's a few feet in diameter, but it's made out of all these triangles so that no matter what angle you hit it from, it always goes back the direction it came. It was pretty cool.
But I mean, the most efficient laser that's been built so far, from I think it's under a mile already. The spread is something like a meter. I mean, it would cover a laser pointing at the moon, and it would spread to the whole of the moon. Though it's called coherent light, it's not actually a thin beam that thin all the way. It spreads like any other beam, laser light.
It's a narrow beam antenna. That's a point where most people are confused.
Okay. Let's see it now. Just getting with your presentation. So we were talking a little about whether length contraction occurs, and I did notice that you had that explanation of the space shuttle getting like half the size. Although my comment on that would be, it doesn't matter what the size of the spaceship is, it would maintain its same velocity. So it's not like it would have to travel twice the distance or anything like that.
It would have to double. It would have to double its velocity to get to do twice the distance.
No, it wouldn't have to double its velocity. That's what I'm saying. Is that if I have a spaceship orbiting the moon, it doesn't matter whether it's the size of the Space Needle or whether it's the size of the pea. It's traveling at the same, 300 miles per hour or whatever, and it just doesn't matter what size it is. It doesn't matter how many lengths of the spaceship it has to travel over unit time. The only thing that matters is its actual speed. whether it's Space Needle or a P, it's going to travel at the same speed.
But you,
Okay, I got a question for Clive.
Just 1 second. I think it's presumptuous to say that it would be the same velocity because the engines would be half the size and they're probably only pushing it half the velocity.
No, I mean, maybe that's the difference, but I wouldn't say that. Not that I'm convinced about length contraction. I haven't seen anything convincing that shows that anything can. I mean, it's obviously, even from Einstein's explanation, just a change in perspective, this whole length contraction thing, and that there's no actual contraction. It's like if I go like this to your head, it's like, am I squishing your head, right? No, you're not. I'm just like,
no, it's nonsense.
Yeah, it's nonsense. So I think we can say that that's kind of nonsense. Let's see here.
So Clive, what's the resolution in your mind of this problem?
The resolution is that physics has got to think about some of the fundamental laws and reject them.
Do you mean you're going to reject Lorentz transformation?
Yeah.
And if you do, what are you going to replace it with? And what are the people who are like doing accelerator experiments that rely on those things?
Well, what they're not relying on for is to compare. The Lorentz transformation incorporates Pythagoras. And my view is that Pythagoras is irrelevant when applied to the views of two observers to an event. So if you take Pythagoras out of Lorentz so that it goes back to its earlier arrangement of figures, maybe it's useful. I'm not sure how it's used in accelerometers, but it's certainly no use in demonstrating that time changes for and lifespan changes for particles. That won't be the reason of any change.
Okay, well, we're getting towards the end of our discussion here. So I thank Clive Tickner for participating in the chat. Clive, is there any place that we can go to read more about your theories? Do you have a website or a book or anything?
Well, I've got a dozen papers published on the General Science Journal.
So the General Science Journal. So if we search your name, Clive Tickner.
Yeah. Do you know that?
General Science Journal.
Do you know that online magazine? Do you know the online magazine General Science Journal?
General Science Journal. Well, I've heard of it.
It's got a lot of heavy hitters writing for it. If you go to GSJ, General Science Journal, and then it has list of authors, and then if you look for Clive Tickner, I wouldn't bother with the earlier ones, but the later ones are quite useful.
Okay. Well, thank you, Clive, for presenting. I hope you got something from it, and we're all trying to learn about this whole time thing, and you've got a couple different opinions. Yeah. So, but that will do it for this episode of today's Science Chat.